Hello everyone, we're very happy to have you with us for this webinar on thermal performance of exterior wall assemblies. The objective of this presentation is to demonstrate the conditions that will increase thermal performance of exterior wall assemblies. We'll discuss thermal bridging and continuous insulation, code requirements, U-value, and present results from thermal modeling of exterior insulated and split insulated exterior wall assemblies. Designers, professionals, and building owners all care about building energy performance. Obviously, no one wants the energy used for heating or cooling a building to be lost because of bad thermal insulation strategy or through assemblies that suffer from air leakage. Codes require that the performance of our assemblies and the overall building be optimal. There are different requirements regarding the amount of insulation for different areas of buildings and for energy consumption of all kinds of powered devices. One of the requirements of recent years pertains to the use of continuous insulation in buildings. The concept is simple: limiting, if not eliminating, thermal bridges. No connection must exist between indoor and outdoor to prevent thermal leakage by conduction through the materials. In some types of construction, elimination of thermal bridges poses great challenges. It is the case for the project shown on this picture taken in Montreal, where we can see the concrete floors that extend outdoors and will inevitably be exposed to very cold air outside in winter. Of course, a large amount of heat will be lost through these floors. Some building assemblies, like this one, raise great challenges to improve the thermal performance of exterior walls. Allow me to briefly put walls aside and talk about roofs. The concept of thermal bridging may be easier to explain with roofs. Let's use the example of a conventional low-slope roof where regularly spaced fasteners are used to hold in place materials such as insulation boards. Fasteners are composed of a metal screw and a metal plate, both very good heat conductors. Each fastener goes through the roof system from just under the roof membrane on the exterior side all the way down to the metal deck located inside. In winter, after a light snowfall, a thin layer of snow accumulates on the roof. This is what you might observe when you look at that roof. On this image, at the location of each fastener, there is an important thermal bridge that allows a significant amount of energy to escape the building. What's happening? The snow melts where plates are present throughout the roof. By changing the mechanically fastened system to one using adhesive, we greatly reduce or eliminate thermal bridges. Consequently, a roof assembly where insulation boards are adhered will significantly reduce energy losses due to thermal bridges and increase energy efficiency of the assembly. On a roof, it will be visible. The thin layer of snow will remain intact. Now, it's not that common to see a thin layer of snow staying on a wall to illustrate thermal bridges, but the concept is the same. If the exterior wall suffers from significant thermal bridges, there will also be energy losses that may not be visible, but will have an impact on the building heating or cooling bill. In an assembly like the one shown here, the concrete floor is not extending to the outside. It is rather interrupted by continuous exterior insulation that breaks the thermal bridges. Thermal leakage throughout a structural component is mitigated by the presence of external continuous thermal insulation. The code gives minimum performance requirements for the energy performance of various assemblies, including exterior walls. Here is a table extracted from the National Energy Code for Buildings, NECB. The requirements are clear. A minimum of energy performance must be provided by walls to offer homeowners energy-efficient buildings. There are several tables like this one in the code. In the case of exterior wall assemblies, the requirements are based on overall thermal transmission and apply to all climate zones in the country. Thermal transmission, also called the U-value, must not be confused with R-value. Let's look at the difference. There are two parts in this expression: global and transmission. The global part means that all materials in the assembly must be considered. A wall assembly is made of different materials, not just insulation. Structural materials, fasteners, adhesives, and air spaces contribute positively or negatively to the overall thermal performance of a wall assembly. Metals contribute negatively by allowing conduction, so less resistance and better heat transmission. Insulating materials contribute positively to the overall performance of the assemblies. Their presence increases thermal resistance and reduces heat transmission. Let's use as an example a simple exterior wall consisting of thermal insulation located between vertical steel studs and horizontal steel blocking. If we look at this wall with an infrared camera in winter, from the outside looking in, the space between the studs is blue. This indicates that where there is insulation, there is less heat loss, whereas near the studs, color becomes yellow or red. And at this point, we understand that there is a greater amount of heat that comes out of this wall assembly because of the poor thermal performance of the steel studs. The U value is the overall thermal transmission. To determine the U value, one can take this assembly and cut it into multiple small sections, creating a grid. Each square of this grid provides its own contribution to the overall performance of the assembly. The U value is the result of the addition of the contribution of each small section in the assembly. The second part in the NECB expression is transmission. The U value represents thermal transmission, the reciprocal of thermal resistance. In other words, U value equals 1 over effective R value. We're used to talking about the R value of materials. For example, an insulation material may have a thermal resistance of R20 or R25. The higher the R value, the more efficient the material. For an assembly, performance is linked to U value, which goes the other way. Like when we play golf, we must shoot low for U value. The lowest U value means that the assembly is the most thermally efficient. NECB requires maximum U values. Let's bring back the simple wall assembly presented earlier. If this assembly is simply composed of insulation positioned in the cavity between the studs with no continuous external insulation, here is a typical image when looking at this assembly with an infrared camera. Adding continuous exterior insulation will cause this change. Thermal conduction through the studs will be mitigated because the studs were covered with a continuous insulating material used over the entire surface. There will be fewer hot spots, and the few remaining will be yellow and much smaller than without continuous insulation. But how much continuous insulation is needed? What is the impact of using continuous external insulation? In order to find out, we looked at studies published in recent years. Based on the work done by engineering firm Morrison Hershfield, BC Hydro published the Building Envelope Thermal Bridging Guide. We contacted Morrison Hershfield and asked them to extend the work that led to the guide. They performed model calculations for us, and part of these results will now be presented. Thermal modeling of exterior wall assemblies was performed under various conditions in order to evaluate the impact of the amount of exterior insulation, the amount of cavity insulation, and the level of thermal bridging on effective R value of the assemblies. Results were then compared to NECB requirements. All assemblies shown today are based on 2x6 steel studs spaced 16 inches on center. Some assemblies use exterior insulation only, whereas others are split insulated assemblies with both exterior and cavity insulation. Hygrothermal performance, air barrier, and vapor barrier positioning are not considered. Focus is made on thermal performance only. When using continuous exterior insulation, a generic material is used. This study is not meant to favor a type of insulation over others. The important thing is to obtain a target R value, say R25. This can be done with mineral wool, XPS, polyiso, or sprayed polyurethane foam. It doesn't matter. Different types of insulation may reach R25 using a different thickness without any impact on the final results. The thermal contribution of the airspace is considered, but not that of the exterior cladding. Here is a first assembly that was modeled. We know that this wall assembly should never see the light of day, but we needed an assembly suffering from significant thermal bridging as a starting point. With such a system, using vertical Z-girts aligned with the studs at every 16 inches, we obtain a U value of 0.47 or an effective R value of 11.9. We put a nominal exterior insulation value of R25, but end up with an effective R value of only 11.9, a pretty high loss. Even if we added external insulation up to R40, it would not be enough to meet the code requirement. One lesson to be learned is that continuous exterior insulation must be continuous. If insulation is interrupted every 16 inches by a piece of metal, as in this assembly, we do not hit the target, and that's why this assembly is so inefficient. For a slight improvement, we used a generic rail system with clips instead of using Z-girts. The difference between the previous assembly and this one is simply the cladding attachment method. With clips spaced 24 inches on center, still with an R25 continuous exterior insulation, the assembly reaches an effective R value of 18.9. This improvement is a step in the right direction and makes it compliant with NECB in Zone 4, the least stringent zone in Canada. If we change the assembly once more and reduce the importance of thermal bridging again by using brick ties, which means brick cladding will be used to complete the assembly, the effective R value reaches 21. This is a definite improvement that is clearly linked to the reduction of thermal bridges. This assembly is compliant with NECB in Zones 4 and 5. If we compare the three assemblies, the effective R value goes from 11.9 for a really ineffective system to 18.9 and then to 21 for a more effective system. The percent retention of R25 nominal external insulation is indicated for reference. Retention improves from less than 50% to almost 85% with treatment of thermal bridging. There are other ways to improve the thermal performance of assemblies. It helps a little if the steel studs are replaced with wood studs. Results will also be better if thermally broken clips are used. The relationship between the nominal R value of the exterior insulation and the effective R value is almost linear. For the lowest performing assembly, the curve slowly flattens as nominal external insulation R value increases. The three assemblies are compared in this graph. The blue curve is the assembly with Z-girts, the red curve is the assembly with rail and clips, and the green curve is the assembly using brick ties. For a given nominal exterior insulation R value, say R25, it can be seen that the contribution of thermal bridges is much greater than that of the amount of insulation used. The lesson here is that rather than trying to add insulation, look for a method of reducing the level and impact of thermal bridges within wall assemblies. Another way to improve performance is to also add insulation in the cavity. Let's use the same three assemblies seen before, but instead of making exterior insulated assemblies, let's add insulation in the stud cavity and create split insulated assemblies. In our example, R20 insulation is added to the assemblies either by addition of fiberglass batt or cellulose fiber insulation. What will be the results of continuous exterior insulation at R25? In the case of our most inefficient assembly, effective R value goes from 11.9 to 18.6. This is just enough to meet the code requirement. Again, this assembly is so bad in terms of thermal bridging that it should never be used. If we add the R20 insulation in the cavity of the next assembly with rails and clips, effective R value reaches 26.6, which is sufficient for code compliance in zones 4 to 6. With the assembly using brick ties, we reach an effective R value of 28.3 after adding R20 insulation in the stud cavity. Again, that is more than what the code requires for zones 4 to 7. If we compare the three split insulated systems, we see a relatively modest increase in performance. Looking at percent retention of insulation nominal R value, R45, for the three assemblies ranging from 41% for the first assembly to 62% for the best performing. The percent retention results are much lower here than they were in the former trio. We'll shortly see why. The impact of the exterior insulation R value in these assemblies also translates to a mostly linear relationship. The difference between the assembly that has no insulation in the cavity and the one that has is about R7. So, the space between the blue curve and the red curve at a given amount of external insulation remains constant. It indicates that the addition of R20 in the cavity of this assembly provides only an additional effective R7. It's not much, but it may allow an assembly that does not have cavity insulation to become code compliant. Here's a recap of the 6 assemblies that were presented so far. Between the upper series, assemblies without insulation in the cavity, and the lower series, where insulation has been added in the cavity, the percent retention numbers decrease. They decrease because the added insulation is, here again, discontinuous. The difference on the left is small because the assemblies all use discontinuous insulation, but on the right, the difference is significant. Although R20 is added, in fact only effective R7 is achieved because the metal frame interrupts the ability of the insulation to do its job. There's a metal component allowing the heat to escape every 16 inches. The table shown here indicates the thickness of exterior insulation required for the exterior insulated assembly using brick ties to be code compliant in all Canadian climate zones and for various types of exterior insulation. Note the significant thicknesses required, which may reduce the practicality of these assemblies. Here is the same information, but for the split insulated assemblies that used insulation in the cavity in addition to the continuous exterior insulation. Required thicknesses are significantly lower because of the addition of cavity insulation. We also wanted to see the impact of adding a bit more insulation in the cavity. Let's model an assembly with R25 exterior insulation and a combination of cavity insulation technologies composed of 2 inches of sprayed polyurethane foam and the remaining space filled with cellulose fiber. This assembly provides R24 of insulation inside the cavity. This assembly reaches an effective R value of 32.6. We can see in a graph that from an assembly without insulation in the cavity to one with an R20 then R24 cavity insulation, there is a quasi-linear progression of the energy performance of this assembly. In summary, we must design keeping in mind the goal of lowering the U value, increasing the effective R value, so that wall assemblies are as efficient as possible. In order to do so, integrating continuous insulation is key while making sure it is continuous. It is essential to mitigate thermal bridges because they have a significant impact on the building assembly total performance and sometimes more significant than the type and amount of continuous insulation. This concludes the webinar. Thank you for watching. We hope you found the webinar informative and certainly hope that we can do this again in the future. In the meantime, we invite you to visit Soprema's website to learn more about our products.